All right, welcome to chapter 5. This is one of my favorite chapters, nuclear chemistry. Unfortunately, we're not going to get too deep into it, but I am going to give you a few quick little tidbits of nuclear chemistry information, especially those of you that are going into radiology. You really got to know a little bit about this because your patients will be like, wait, what, nuclear or something? So make sure that you're able to kind of talk to them about this. So nuclear chemistry. So radioactivity is really the key here to nuclear chemistry. So what is radioactivity? It comes from unstable nuclei. So nuclei is the correct plural term. Nuclei that aren't stable, meaning they don't have a good proton to neutron ratio. So think about what holds a nucleus together. So I have protons in the nucleus. Look at these two protons. What do you notice about the two protons that might cause them to be unstable? Right, these protons are both positive and they repel each other. So we got to add in some little neutrons in here to keep it all together, right? It actually creates its own little gravity to hold everything in. And so the nucleus is a very delicate kind of thing. Too many protons or too many neutrons can cause it to rip apart. That's nuclear fission. Sometimes you can also have particles that run really high temperatures and they run into each other. That's called nuclear fusion. And so you get radioactive unstable versions of elements if they are, they don't have this stable proton to neutron relationship. So what they do is that they emit radiation. So they give off pieces of themselves and those fly through the air and they go around and they kind of wreak havoc on existing molecules and atoms. So if you have a particle flying at you, it knocks your electron off. Now you're charged. What kind of charge would you be if a particle from one of these radioactive things, it split open and it lost part of itself? It flies at you and knocks your electrons off. What kind of charge would you have then if your electron got knocked off? Your charge would be positive now. And maybe you were supposed to be neutral and now you're positive. So now you have a totally different dynamic, right? You're attracted to negative stuff when you should be not attracted to anything because you're neutral. Or maybe you were negative, supposed to be attracted to positive stuff. They knock an electron off you and now you're neutral. So it definitely changes how our proteins fold and all this kind of stuff. So, ionizing radiation is not great. But we actually have more of it coming at us right now than you think. We're capable of dealing with quite a lot of ionizing radiation before it causes harm. If you're super interested in nuclear chemistry, you should definitely watch the Chernobyl series. It is terrifying, but the science in it is really good, and it is really interesting. So I actually learned a lot that I didn't know about nuclear chemistry from the show, and then of course did my own research to find out is that true. And the science in it is very good. So highly recommend the Chernobyl series if you can watch it if you're interested in nuclear chemistry. So for example, we would call a radioactive isotope a radioisotope. And this is an example of a radioisotope used to treat thyroid disorders. We use radioactive iodine for this. And so this is iodine 131. If you recall from the last chapter, this is how we would write that isotope notation for that. And then here are some elements that have some radioisotopes. So magnesium has a stable version. It also has some radioactive versions. Iodine has a stable version, but we use one of the radioactive versions in treatment of thyroid disorders. So radioactivity can be good if we utilize it in a certain way. Uranium has no stable isotopes. It's only radioactive, but we only use uranium-235 for any sort of nuclear reactions because 238 doesn't have quite the properties that we need. So when you hear about countries or if we're enriching uranium, that means that we're separating the uranium out and getting only the uranium-235 that you need to build nuclear bombs and stuff. So there's different types of radiation that I want you to know. So these are kind of just definitions. Alpha particles, beta particles, positrons, and gamma rays are what you need to know. So these are also called beta minus and these are also called beta plus. So just kind of giving you that info. An alpha particle is really just a helium nucleus. So what's happening in the nucleus here is that the nucleus is unstable, and it's just kind of like cutting off part of itself and just spitting it out. So it spits up that alpha particle. It has a mass of 4, an atomic number of 2, and it's identical to a helium atom. So you'll see us write it like this, or you'll also maybe see, when I say us, I'm saying chemists write it like this. That's also acceptable. A beta particle is kind of like an electron, just a high energy electron. And essentially what happens with the beta particle is the protons, there's too many neutrons. There's too much neutral stuff going on. So we need more positive stuff. So imagine a neutron is kind of a combination of a proton and an electron. So if you want the neutron to go away, if it gets rid of its electron, it's now just a proton. So your neutron turns into a proton and gets rid of a negative part of itself. So it gets rid of this beta particle. So this is beta particles are emitted if you've got too many neutrons in your nucleus. It's not stable because there's too many neutrons in there. Alternatively, if you have too many protons and not enough neutrons, your protons are repelling each other. I mean, this can also happen where if you have too much repulsion, it literally just splits into an alpha particle. You just knock part of it off. But sometimes you can have a proton turn into a neutron. So that proton is going to have to get rid of its positivity to become neutral. So it gets rid of a positron, which is like a positive version of an electron. And then also you have gamma radiation, which comes out with some of these other forms of nuclear emission. Now, a couple words I want you to know here. Emission means give off. Also, you can think about it as emit. Decay means breaks into or breaks apart. So all of these words I might say like, oh, this undergoes alpha decay. That means it breaks into an alpha particle. This undergoes positron emission. That means it gives off a positron. So all of these things are kind of similar. These are all products of a nuclear reaction. You can also have protons or neutrons be emitted. You could just like spit out a proton or spit out a neutron, but y'all already kind of are familiar with that. So this here, just looking at like the symbols we might use. So you may be interested in the biological effects of radiation. Unfortunately, we don't have time in this class to like super duper get into it, but what happens is, I was kind of telling you earlier, is that the radiation comes out of the radioactive isotope and it hits electrons of things in your body and it knocks those electrons off, making now these ions where there weren't supposed to be ions. Those electrons that got knocked off, they go in and they react with something else over here, causing other things to happen. So it just kind of, everything was working, and then you kind of just start knocking things off and adding things to where they don't need to be, and it gets a little chaotic in there. So it overall, it damages cells. It causes chemical reactions, it messes up chemical reactions, and it's just damaging to cells. Alpha particles are stopped by a piece of paper. So if you're wearing clothing, alpha particles are not going to get inside your body. Beta particles can go through a little bit of tissue, but they can usually be stopped by several layers of skin. So like your skin is a pretty good block against beta particles from getting inside your body. But gamma radiation, that's just energy. It's not a particle necessarily. I mean, it has photons in it, but it's not like a full like particle you can really measure. It goes through all the way through your body. And so it's in Chernobyl, it was the gamma radiation that was really harming people, because it was just like penetrating through walls and everything, right? So you can kind of see here how far it can travel in the air, how far it can travel in tissue. Now notice the alpha particle can travel inside of you if you ingest it. You could find alpha particles in your smoke detector. So there's a little like radioactive element in your smoke detector, but make sure that you don't eat it. It's fine to have in your house. It's not going to harm you, but if you eat it, it can get through some of your tissue. So it can penetrate some tissue a little bit. And then carbon-14, you actually have that in your body right now. So every carbon, every living thing has some carbon-14, and there's a decay pattern of carbon-14. So when you die, you stop making you stop taking in new carbon, and so the carbon-14 starts to decay over time. When I say decay, it means turning not into carbon-14 anymore. So if a nuclear atom goes through its radioactive process, it decays or it emits something, it's no longer what it was. So when carbon-14 emits a beta particle, it's no longer carbon-14. So what happens is that carbon-14 is constantly decaying, and I'm taking in carbon as I breathe and as I eat, right? So I'm constantly renewing that carbon-14. Then when I die, I stop taking in new carbon. So the carbon-14 starts decaying without anybody to replace it. So how much carbon-14 is left tells scientists how old my bones are, because they know how long ago I stopped eating and breathing and taking in new carbon. It's how we date things. It's pretty cool. A nuclear reaction, this is kind of where your math comes in. So your study assignment 16 is going to dig into this a little bit. So if I say that uranium-238 goes through an alpha decay, that means it gives off an alpha particle, and we have to figure out what this other particle would be. I want you to look at a couple of things. Do you see how 146, I don't really want to look at neutrons and protons. Actually, I want to look at the whole number. So let's kind of pull these numbers out. This 238 on top and this 92 on the bottom. And it's kind of equal to 234 over 90 plus 4 over 2. Probably should do this in a different color, but I'm going to kind of highlight my writing here. So 238 is equal to 234 plus 4, right? 92 is equal to 90 plus 2. So that's how we figure out what this new nucleus is. Whatever it needs to be to make this all add up on both sides. So let's do a little practice because it's kind of hard to explain this. So I'm going to let you see if you can figure out what goes in here. I'm going to give you 3 blanks. So I want you to fill out each of these blanks. So looking here, putting an X for this first blank, it's going to be whatever's on top is going to have to add up. So 251 is going to have to be equal to whatever my X is plus this number 4. So what is X? So X is equal to 247. Okay. And then do your numbers first. So filling out this bottom number, 98 is equal to X plus 2. What is X? X is 96. So I get a 96 to go here. Now, this is going to kind of be like an isotope notation. Which one of these numbers is going to give me the identity of the element? It's going to be this bottom number. That's the atomic number. So we look on our periodic tables and find number 96. Number 96 is Cm, curium, after Marie Curie. So that's what we make. So that's kind of how I'll be asking you these questions. We're going to fill in the blanks, kind of. So this is a alpha. So I would write this as CF251, californium, undergoes alpha decay. It's kind of how this would be, how this might be written in sentence form. And you would write this equation out. So yeah, so another alpha decay. So let's practice using the words. Go ahead and practice this one. This is the reaction that happens in your smoke detector. Americium-241 undergoes alpha decay. Let's write the balanced equation. So remember that this tells me the mass, and I need to use my periodic table here. So I look here and I find that americium, Am, I know it's number 241. Don't change it based on the periodic table. Remember, the mass and the average mass can be different, and that's okay. I see that it's number 95. And it undergoes alpha decay, which means that the alpha particle is a product. And if you're decaying, you're breaking down. So the americium is breaking into an alpha particle plus something I don't know. So let's figure out what that thing I don't know is. So I'm going to look at both of my number systems on top. So 241 is equal to 4 plus what? And 95 is equal to 2 plus what? Isn't this nice math compared to some of the math we've been doing? So we're going to plug in here. This is going to be 237, and this is going to be 93. Which one of these numbers tells me what element it is? Right, the 93 tells me because it's the atomic number, and I see that's Neptunium, named after the planet, Neptune. That's your reaction. That's it. So beta decay, again, we're taking we have too many neutrons, so we're making a new proton. So I'm actually going to change not the mass anymore because I'm just getting rid of an electron essentially, but I am going to change the atomic number. So let's practice this one. So potassium 42 is a beta emitter. Try it. Okay, so let's look at this. Potassium is K, 42 is the mass. So I'm going to say 42 on top, then K. What's the atomic number for potassium? I need to look at this up. On your study assignment, they don't give you those atomic numbers. The bottom left numbers, you need to write them down because they're going to help you with the math. So atomic number is 19. It's the number on top. And it decays or emits. Also decay, meaning the beta particle is a product. So I'm going to write 0, negative 1e plus what? We're going to figure out what goes in the blank. 42 is equal to 0 plus x. Well, that's pretty easy. That one's going to be 42. And then I have 19 is equal to negative 1 plus x. Don't let this negative 1 get y'all fooled, because I have a lot of students that will get fooled by this. So we know it's a 42 up here. Okay. Did you put 18? Try 18. 18 plus negative 1. What does that equal? That's really like saying 18 minus 1. Is that 19? It ain't 19. It's 17. What goes in this blank? 20. So what element is number 20? Calcium. So make sure that you're not get some easy math and then we just forget everything we've learned. So here's another example of a positron emission. Same idea. You just kind of put the particle where it needs to go and then you fill in the rest. Gamma radiation. Sometimes we use this little M to show that we have some gamma built up in the element and we're just going to release it. And then a little summary table for you. So transmutation is just a word that you might hear especially if you're going into radiology. Sometimes we can make a particle radioactive that's not radioactive. If we slam an alpha particle into a stable nucleus, it can turn into radioactive things, and we can make things radioactive that aren't. So this is kind of how we do like nuclear bombs, as we kind of take these particles that are, a little radioactive and we make them a lot more radioactive, and they give off a lot of energy whenever they do this. So every time we do any of these radioactive things, we give off a lot of energy. So we can practice bombardment. Bombardment just means you're going to add the particle as a reactant, not as a product. So add it on the left side. So we're going to try this question. So let's see a bombardment of nickel 58 by a proton. So I know I'm dealing with nickel. I know its mass is 58 because they tell me that. I'm going to fill in my atomic number by checking my periodic table. Oh, that's 28. I'm going to bombard it, meaning I'm going to add a proton to tell me what it is. And it produces a radioactive isotope, which I need to figure out what that is, and an alpha particle. So that tells me I produce an alpha particle. So what goes in the blank? So it's a little more complicated for this one because we got 58 plus 1 equals 4 plus x, and then we have 28 plus 1 equals 2 plus x. So here we get 59 equals 4 plus x. X is equal to 55. And here we get 29 equals 2 plus x. X is equal to 27. So my answer is 55 over 27. 27 is the one that gives me what it is, which is cobalt. Yep. Just a little addition and subtraction, but you're doing nuclear chemistry right now. Pretty cool. So how do we measure like radiation? We measure with a Geiger counter. So if you've watched Chernobyl, they kind of go down and they're like, clicking these things around. Those are Geiger counters. What they do is that they kind of have this meter, and then the radiation kind of goes in and excites the electrons and it causes the meter to change its detection. You don't need to worry about doing any math with these. I just want you to have seen them, especially if you're going into nursing or radiology at some point. You can kind of look back on these notes. Curies are a measurement here. Becquerels are also another radiation activity. Rads are the radiation absorbed dose. It measures the amount of radiation absorbed by your body tissues per gram of material. And then the REMs are the radiation equivalent in humans. And so REMs are really kind of what you're looking for with how dangerous is it to humans, not just to any tissue. So the REM dose is kind of how much doses of radiation that maybe your patient has gotten. The absorbed dose, the RADs, by some kind of factor is your REM. So notice that these factors are a little bit different for different particles. For beta and gamma radiation, the factor is 1. So the absorbed dose and the equivalent in humans is the same. But check out those alpha particles. The factor is 20. I just told you alpha particles can be blocked by a sheet of paper. So why do you think that alpha particles have such a high factor for damage? So like if I ingest an alpha particle, it's 20 times more dangerous than if I ingest a beta particle. Why do you think that is? The reason is the alpha particles are really big. So if they get into my body, they're going to be like a bull in a china shop. Versus beta particles are really small. They're going to go through my tissue they're going to do damage, but not that much damage. And so this factor is kind of, giving us an idea of why it's bad to ingest any sort of radioactive material, right? Another, some things of if you're going into the healthcare field, you may see these on like the side of an MRI machine or something, just giving you a little bit of text here. I'm not going to ask you to memorize or use any of this. There's just some conversion factors, which you could use if you needed to. So just if you're kind of like scared of radiation now, so lethal doses of radiation, so the LD50s for some things for humans, it's 50% of humans are killed by 500 REMs. Look at this table. What does MREM mean, you think? It means millirems. So each of these is a millirem, and this is 500 REMs. This is 500,000 millirems it takes to, so you have to add these up to 500,000 before you get a lethal dose, really, essentially. So the ground gives off 20 millirems. You're going to avoid the ground because you can't, right? If you ever are air travel, you get in a plane, you expose yourself to some millirems there. Don't expose yourself to radon, and try not to have a lot of upper GI x-rays because those are pretty big, because they can't really protect you with that heavy lead blanket, right, when you get an upper GI x-ray, because they need to see it. But if you get like a hip x-ray or a dental x-ray, it's not really that big of a deal because they're protecting the rest of your body with that big lead blanket, right? But if you do work in an environment where you are giving x-rays, you always have to stand behind that wall of concrete or that wall of lead because the x-rays cannot penetrate that. So do not stay in the room with your patients because you are exposed to x-rays more. They're only exposed to the x-ray for like a second while you take the x-ray picture. So make sure that you are definitely following the instructions for protecting yourself against those x-rays. Because you imagine if you stayed in the room with every dental and you kept getting 20 and 20 and 20 and 20 and 20 for multiple times a day, right? That's going to add up for you. So the last thing we're going to talk about here is half-life. And I don't want you to think anything more about half-life than what it is. It is the time it takes, do not have to get real technical with this, for half of the substance to go away, or to turn into something else, right? So if I start with 20 milligrams of my iodine 131, after one half-life, I'll have half of that, which is 10. After another half-life, I'm going to cut this 10 in half to get 5. Now I got 5. Another half-life, I got 2.5, because that's half of 5. So each time, I'm dividing by 2. So how long does it take for me to get to 2.5 milligrams of iodine if I start with 20? It takes 1, 2, 3 half-lives. Well, how long is a half-life of iodine? You can find that here. So the iodine has a half-life of 8 days. So let's look back at this. How long would it take me to go to 2.5 milligrams? So if this is 8 days, this is 8 days, and this is 8 days, it would take me 24 days to get down to that level, right? That's exactly how we do half-life math. Half-life is exponential, so you cut first in half, then you cut the second in half, and the third in half, and the fourth in half, the fifth in half. Eventually you kind of get to the point where you're kind of pretty much zeroing out at some point. I think after like 10 half-lives, you're probably very close to 0. Notice that carbon-14 has a very long half-life, which is why we can tell the age of dinosaur bones, right? Because it's got a pretty long half-life. So some medical stuff, notice that, they don't have quite as long of a half-life, but you do want something that has a little bit longer of a half-life, because the longer half-life it is, the less dangerous it is. So you don't want to be dosing your patients with things with like really short half-life. So like if you can avoid dosing your patients with technetium, that's good. So like, thinking about these like iron and iodine, it's not so bad for your patients as far as like their level of radioactivity exposure. So here's how I can ask a question about half-life. So read this over and see if you can figure it out. So my strontium-90 has a half-life. So I'm going to write out some conversions here. One half-life is equal to 38.1 years. I have 36 milligrams. So how many milligrams after 52.4 years? So I have to think about this kind of in 2 sections. First, how many half-lives have gone by in that time? So type 1 half-life problem. First is find the number of half-lives. Then apply the number of half-lives to get amount left over. Okay, so these type 1 half-life problems ask you how much is left, how much sample is left. So first let's find the half-lives, and I'm going to use dimensional analysis for this. So if I know that one half-life is 38.1 years, well, how many half-lives have gone by? It's going to be 4 half-lives, right? So the second step is to now apply that 4 half-lives. What does that mean? We're starting with 36, and we're going to cut it in half. How many times are we going to cut it in half? 4. Let's cut it in half one time. What's that? What's that going to be? Do math. 20, 13? No, that's not right. Yes, that's right. No, it's not right. My brain was not working. 18. Okay, now we're cut that in half. 9. Cut that in half. 4.5. Cut that in half. 2.25. So how much do I have left after 4 half-lives? 2.25. So if they ask you how much is left after X amount of time, first find out how many half-lives are in that time period, then apply those half-lives. Cut it in half that many times. So here is another half-life calculation. They tell you how many years old it is, the half-life, what fraction of the half-life has passed is a little bit more difficult. But this is just a a fraction conversion. So I'm just going to show you really quick. So if the half-life is 57 years, what fraction of the half-life has passed? Well, if it's 2,000 years old, this is one half-life, just a fraction, right? It's about 0.35 of its half-life have gone by. So it's not even halfway done with its half-life yet. I just want to show you one more example. I thought I had one in here. Just like an extra example of another half-life problem. So I'm going to say type 2 half-life problem, and you're going to see this on your study assignment. So you will have plenty of practice, I promise. And this is going to be if it says how much time has passed. So they're going to give you a beginning amount and an end amount, and you have to figure out how many times did you have to cut that in half. So how many times did you cut in half to get that amount? That's the number of half-lives you did. Then step 2 comes next. Then you take the number of half-lives and you figure out how many actual years or days or minutes or whatever that is. So it's kind of the opposite. So if I said, for example, hey, 36 milligrams has turned into 2.25 milligrams. The half-life is 38.1 years. How long did this take? So you would say, well, I know 36. How many times do you cut it in half to get to 2.25? Well, I cut it in half one time, I get 18. I cut it in half 2 times, I get 9. I cut it in half 3 times, I get 4.5. I cut it in half 4 times, I get 2.25. So I cut it in half 4 times, 4 half-lives, okay? So my second step is to say that 4 half-lives, if every one half-life, they give me this table or they give me it in the question. So how many years would that be? Well, we've already done this, right? So it's going to be 152.4 years. So I'm going to just showing you the opposite way of solving these half-life problems. It's going to be one or the other. So some medical applications. This is a PET scan. We use these with this a thyroid scanner. We use positrons in PET scan. That's what the P stands for, positron. You also use what is it? We use treatments for things. Can be radiation can be helpful. These are PET scans. This is a CT scan, and you use dye with the radioactive dye to kind of make things show up on the CT scan. And then in MRI, we use a dye as well. And so all these use radioactive things, or the instrument itself has some kind of radioactivity in it to be helpful for your patients.